Hello, everybody. We are going to take a look at our review sheet and see how you are doing. I'm hoping that you attempted this first before checking your answers or coming with questions, because you can't learn if you're just copying what I'm doing. I would first go and try it yourself and then come back and get some focused attention. So that's my biggest advice. Go try it first before getting the answers. Because if you just get the answers, you're not learning anything at all. So we're going to look at our first two data sets. A is our curvy line. And if you have a curvy line, it is going to get longer on a motion map. If you look here, your slope is 0. And then the slope gets bigger and bigger and bigger, and then it goes really fast over here. So A is super duper fast. And what you need to do is you've got to start it at 0 meters in 0 seconds, and you're going to end at 8 meters. And you're going to have a little tiny baby arrow at 0 seconds. And then your arrows are going to be getting just a little bit longer. I do need to make that one a little bit longer. So these arrows are going to get longer. And in a perfect world, I would have made that by 8s. It's not a perfect world. I did my best, and I'm looking for a trend that is increasing. Now, B is a linear line, which means it has a constant velocity. Again, at 8 seconds, starts at 0. And that one makes a little bit more sense here. So this is 0 seconds, 1, 2 seconds, 3, 4, and 5 seconds. Okay, how is A different from B? A is different from B because A has a curvy slope and increases its velocity. B has a constant velocity. Okay, and then we are going to look at displacement. And remember, displacement is on a position time graph, the change on the y axis. So it is the change on the y axis. So if you're looking up here, who has the bigger change on the y axis up to 5 seconds? So here's my 5-second mark up here. And B ends at 8. It starts at 0 and ends at 8. A also starts at 0 and it also ends at 8. So they have the same change on the y-axis, same change. So they are in fact equal. Okay, displacement from 0 to 2.5 seconds. So at the halfway mark, who changed the most on the y-axis? So B is this line right here at 2.5 seconds. So this one went up that far. So that's a pretty big chunk. And A only went up that far. So it's a little tiny change. So who had the bigger change? That would be B. Displacement from 2.5 to 5 seconds. So B went from this point to this point, and then A went from this point to this point. So who had the bigger accelerate or the bigger change? That bigger change would actually be A. The average velocity from 0 to 5 seconds. This is your final position minus your initial position over your change in time. So 0 to 5 seconds, they are both having 5 seconds. They both start at 0 and they both end at 8. So they both are at 0 and they both end at 8. So they both have 8 over 5 slopes, which is the same. So that's going to be equal. Average velocity from 0 to 2.5 seconds. Okay, your velocity is the slope, remember? So who has the steeper slope from 0 to 2.5 seconds? And clearly up here, B has the much steeper slope at 2.5 seconds. But who has, let's get this all the way down here, who has the instantaneous velocity at 5 seconds? So if you look right here, who has the steepest slope? So A, it looks like it's here. B looks like it's here. I would say A has the steeper slope there. Okay, over here, we have two lines, and you will notice that this is a velocity time graph. So this doesn't care where you are, it just cares how fast you are going. And if you remember, displacement on a velocity time graph is the area under the curve. Or the area under the line if there's no curve. Okay. So is A underneath this for 2.5 seconds. A is this whole segment here. B's area is just the triangle. Okay, and A is the whole rectangle. So who took up more space? A definitely took up more space. The displacement from 0 to 5 seconds, again, that's the area. So what you have to do is for A, you have the rectangle, so that is base times height. For a rectangle, you have base of 5 times your height of 4 meters per second, and that is seconds. So you have an area of 20 meters. For line B, I'll make them color coded for those of you that are paying attention. So we've got B is a triangle, so we have to do 1/2 base times height. And I like the 0.5 base times height. So 0.5 times your base of 5 seconds times my height of 8 meters per second. So 8 times 5 is 40. 40, half of 40 equals 20 meters. So look at that. These guys are equal. So who has the acceleration is your slope. Who has the steeper slope at 5 seconds? So the steeper slope at 5 seconds, B is way up there. Velocity is way down here. I would say that that's B. You could also find the different slopes. So the slope of A is 0 because it's a flat line. And the slope of B is going to be something positive. It's going to be what, 8 over 5? So whatever 8 over 5 is, it's going to be something positive. So anything positive, you've got to, or something with a slope. It doesn't matter if it's positive or negative, frankly, but if you have a slope, you've got a good graph with a positive acceleration there. Okay, these guys. Again, ask yourself 3 questions. If it is stopped, medium, or fast. That will get you to make your velocity graph, because right here is stopped. This one is medium, and this one is fast. And that's in the positive side. You do the same thing on the other side. We have stop, medium, and fast. And that's just in the negative. So over here, I'm going to say that that is pretty fast. And this is kind of medium. This one is stopped. So I'm going to kind of carry my line down a little bit so I can match up my graphs pretty well. The beginning, it is fast and it is positive. So I'm going to go on the positive side and mark a fast dot. Medium is on this line. Boom. And it's still positive. And then it's going to stop at this line. So you're going to have a line like that. Now you have to look at this side. It stops here. So we're still at a stop. And then it's going to go kind of medium here. And then fast. But it is in the negative direction this time. So again, we've got our stop. And then we're going to have our medium. We just got to follow that down. And then it's going to be fast in the negative direction. So you're going to have something like that. Okay. And then to get the acceleration graph, ask if your velocity time is positive or negative. This one is definitely negative. So I'm going to put a line down here in my negative quadrant. Okay. This one's a little bit easier. Again, we're going to go stop, medium, and fast, and that's positive. And then stop, medium, and fast, and that's negative. So right here, flat-ish slope is stop or slow. And then over here is going to be kind of medium. And this one down here is going to be fast. So at the beginning, it is stopped. This is going in the negative direction. So we have to go downwards to the negative quadrant. That's medium. So I'm going to make my lines match up. And then this line is just past that line at fast. So you're going to have a negative line like this. And then ask yourself if it's positive or negative. It is negative. So you're going to have a line like that. This one I'm being kind of mean because all you have to do is you have to isolate your graph in two places. So again, I break my graph right where we have a break in the lines, a break in patterns. And this one, the velocity is getting faster and faster. So in order for the velocity to get faster and faster, your slope has to get steeper and steeper, and it's positive. So to make it go steeper and steeper, you're going to do something like that. Fast. And then over here, the velocity is not changing, it is staying constant. And if you recall from our time in speed and velocity, that makes a linear line. The first part here, acceleration, is positive. Okay, it's positive. So this is going to be positive up here. The linear is right on the origin because it's not speeding up, it's not slowing down. Okay, my dog spots a squirrel and takes off from rest, accelerating a rate of 0.5 meters per second. So we have 0.5 meters per second, which is our acceleration. It reaches a tree in 5 seconds, so my time is 5 seconds. And what will be the dog's velocity at the end? So your final velocity, we're looking for it. So my word of advice, if you struggle with these and struggle with missing points because you're going too fast, is slow down and take a look at what you're given. You could even have a VI equals 0 because they're at rest, but 0 is not going to impact anything here. So you can do the simple formula of V equals A times T. Now I just do what I call plug and chug. Acceleration is 0.5, that second squared, times my time, which is 5 seconds. So half of 5 seconds, get rid of one of those seconds, 2.5 meters per second is your velocity. Okay. My car can go from rest to 25 meters per second in 10 seconds. So what I'm going to do is go make my scale. This goes 1 all the way up to 10 seconds. And my velocity counts by 5s. You can count by something different if you would like. But I do know that at 10 seconds, it has reached 25 meters per second. And it started at rest, so there's your 0, 0. You're going to make a straight linear line here. It's at a constant rate, so we know it's linear. Acceleration equals your slope of a VT graph. Slope of a VT graph. So you can do y2 minus y1 over x2 minus x1, which is going to get 25 meters per second minus 0 over 10 seconds minus 0. So that's really 25 over 10, which is 2.5 meters per second squared. Create an acceleration time graph using your calculated acceleration. It did not change. It is positive. So I can just say somewhere in here is 2.5 meters per second squared, and it's going to go straight across. And these are going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the displacement? Equals the area under the line. On a velocity time graph. And that's all the way up here. That is this graph, velocity time graph. So we have a triangle. So my formula is 1/2. My base is 10 seconds. And my height is 25 meters per second. So 10 times 25 is 250. Half of 250 is 125. And then we got to look at our units. Seconds cancel, and they leave us with just meters. How fast is the car going? 3 seconds after it starts. The velocity is the area under an acceleration time graph. So that's really base times height because it is a rectangle. And we want to go for 3 seconds. So I'm going to go here, and I'm going to shade in my area. So my base is 3 seconds. My height is 2.5 seconds. And that should get us 7.5 meters per second. All right, we got Jack running along the, speeding up as Jack does. You are going to label your graph, time in seconds, position in meters, and your scale can go up by ones. On your time, and then I liked 5s on my position. And I've got to go all the way up to 50 because his position is 50 meters over here. And I know it's 7 seconds because this is 0 seconds. This is 1 second, 2 seconds, 3, 4, 5, 6, 7 seconds. So at time 0, 0, we're right there. At 1 second, we are at 1 meter. So we're going to be pretty low here. At 2 seconds, we're at 4 meters. At 3 seconds, we are at 9 meters. At 4 seconds, we are at, that's 15, this is 16. At 25 meters, this is 5 seconds. At 6 seconds, we are at 36. And 7 seconds, we are at 49. So you should get a curve something like this. The instantaneous velocity at 4 seconds is something you're going to have to use the mid-time method for. So we are looking at 4 seconds. So 4 is in between 3 and 5 seconds. So we're going to use that mid-time method. So if we're looking at 4 seconds, we need data from 3 and 5 seconds. So at 3 seconds, it's 3 comma 9. And at 5 seconds, it is 5 comma 25. So now we're going to make our slope, which equals 25 minus 9 meters over 5 minus 3 meters. $25 minus 9 is 16 over 5 minus 3 seconds over 2 seconds, which should be 8 meters per second. And last but not least, we have a car going down a ramp, much like your wheel goes down a ramp. And the first thing it wants you to do is describe that motion. And we start at 0 meters, positive direction, increasing velocity, it's speeding up, or accelerating. And let's see, we can also put stops far from 0. So it's going to start slow and then get fast. And again, it's in the positive direction. So it's going to start slow. So we're going to have very little slope. And then it's going to get faster and faster and faster, which means we need a steep line. Over here, we have slow, medium, fast. And again, that's the medium, fast. And this one is slow or stop. And that's just going to line up like that. And acceleration is positive. Over here, you're just going to have little vectors growing into big boy vectors over here. I don't have a specific time frame. I just need to see the trend that they are getting bigger. So to review for your test, please go through all of your old work, be able to answer the questions from your old work, go over that worksheet that is things I should know by now, and hopefully you will have good luck on the test. Thanks for watching.